Good morning. This 4th of December, I'm starting early. It's 9:15. And this is the last problem where we should be able to solve or conclude the Hasse-Davenport relation. And we should take both sides of problem 15, and so I've put that in as well. And I believe we should start using problem 16 to reduce the left-hand side a little. We sum over each degree. That's a D, not an A. So that's the left-hand side. And then by problem 16, this vanishes if it won't write properly. Well, that's all right. If D is larger than or equal to 2. If D is 1, we only have one monic polynomial, namely f is equal to 1, it's the constant polynomial, 1, and lambda of that is 1 times d to naught plus, and lambda, and the sum of all the monic polynomials, and that gave exactly g of chi. And now we have to see which, what are we working on here? So which space should we be using it on? So we have FQ, and we have f of q to the rth, the field of q to the rth elements. I always expected this to be q, to be what we call chi r, to be the one on the field with q to rth elements. I think we have to believe that. So that's the formula that we shall take. There should be a t there, yes. There we go. So we take logarithmic derivative. This is the degree of f minus 1. my. I'll just make a break to make sure which characters and polynomials I'm working with. I just looked at problem 14, where this looks exactly like what this is like, look exactly like this. So that means that we should be able to reduce the denominator times this to being equal to this, then we should be home. What we must find is the constant term not writing very well this morning. The expansion of the denominator gives some powers, but starting with 1, a unity. So that means we have to take the, and of course t gives factors t, so we just take 1, and then times the constant term of this, and that's all of degree 1, so we sum all where degree f is 1. And this is over the irreducible ones. That's what it says here. Of order, oh, that's the same, of course. So it's minus lambda of f, degree f, that's an f, times t to naught. So oops. And this is minus the sum of all the f's of order 1 in fq, which gives exactly g of chi itself. That's a little strange. It should have been to the rth. Well, let's see what I get. The constant term was minus d of chi, and then applying problem 14. Did I have that? No, haven't got it. Then this is equal to the sum, I'll just copy it, d dividing r f being that's the opposite way, being irreducible of degree d, d lambda of f, d times lambda of f raised to r divided by d. So we are getting near my problem is with this expression so this is the right hand side, which comes from the left hand side of this guy. It is actually possible to make an example with the field of 9 elements and then write it all up. And then the error should stand out clearly. I don't know if that's the way ahead. Well, I'm stuck. All right, I have looked it through once again. And first, here we are considering polynomials over fq. And that means that S1 are first order polynomials with constant terms in fq. This means that this guy is g of chi itself. We should write there we have chi goes from fq into the unit circle or into the complex numbers, whichever you prefer. And that means that I have proven 1 equals minus 1. This should just be G as well. That was just a typo. Therefore, the next step is to find where is my error in sign. That's annoying, isn't it? And then this is equal to, I don't think I can write here. This is equal to G of chi r by problem 14. And then we have derived this formula. My method was all wrong. I don't know how to do it right, how to get on with it. I'll just take a break here and get an idea. Maybe I'll be back after I've been playing tennis. Just very quickly, I found the sign in error. We have minus 1 here and minus 1 here. Those two together gives plus. So we just remove this minus, and this minus. Or yeah, and then this 2. So I gave an alternative solution to problem 14. I just had an idea. Expanding this side gives G of chi, the sum of minus G chi t to nth. And if we now choose n equal to r minus 1, and that gives exactly what it says in the problem here, minus 1 to r minus 1 times G of chi to rth. The next problem is that to find the term of order t to r minus first, of order r minus first, of the right-hand expression. I'm beginning to feel pressed for time. There's actually a quarter of an hour until I have to leave, but it takes a few minutes to get ready, and that's enough that I can't think anymore. Hello, still 4th of December, afternoon now, 3 o'clock in the afternoon, and we should start on the right side here. First, I had this idea of collecting or putting everything on common denominator, which is, it's an infinite series, so this is not really very possible. But when I loaded the page, I got the idea to treat every term in its own right and expand it. So let's try that. And let's call d, the degree of f. So we will collect all of those with the same degree probably. Let's see. D t to d minus 1. So we must add all powers of this from 0 to infinity. D only comes 1, and t to nd plus d minus 1. And we have to have the power r minus 1. So let's see how we get d must be a divisor of r, and then that must be equal to n plus 1. Let's write d first. D lambda of f to r divided by d t to r minus first. Now, does that agree with what we should obtain? I haven't written what it must give. The sum d lambda, that's it. So we just have to sum over all the polynomials, irreducible monic polynomials that has a degree dividing r. And then just the coefficient to t to r minus 1 must be equal. So that's it. And this is really 20th century mathematics, handling these infinite series, which in turn gives an infinity of formulas, all derived with one foul slope. And I've just done 2 of them in this problem, namely proving that g of x equals d of x. Now, d of x is given by, this is an alternative proof of problem 14, I think, and then problem 17, which I haven't quite finished, but now it should be clear how to do it. That means that in a course of 4 days, I was able to get through the problems which led to a proof of Hasse-Davenport's relation.